Hello friends and welcome. In this short video we will talk about angular variables, so polar coordinates and a couple definitions of mathematical objects and physical quantities that we'll use when we study rotations and circular motion and simple harmonic motion. And we start with our good old construction of the unit circle, or actually a circle of radius r, and a point on this circle. So we're very familiar with Cartesian coordinates x and y, and I hope that by now you're somewhat familiar with r as the distance from the center to this point, and phi, the angle, phi or theta, or so you will find different notations like this: curly phi, theta, maybe this phi. Sometimes you'll find alpha. Like any angle, any name is fine for angles. And this, by the way, let's emphasize that it's always measured anti-clockwise from the x-axis. And this is a convention, but it's important that we keep this convention, because if we remember this, then we can use the usual formulas to relate r, phi, x, and y, which are the usual sine and cosine, because x is none other than r cos phi, and y is r sine of phi. So if you have r and phi, this is how you find x and y. If you have x and y, then you find r by doing Pythagoras, and you find phi by doing some arctan of y over x. These are the same thing. I'm confident that most of you know this stuff, so this is just a quick recap. But not everybody may know that these r and phi are actually called polar coordinates. And these are a perfectly equivalent and complete set of coordinates, just like x and y. You can express all the physics that you want, both in Cartesian and in polar coordinates, when it happens on a plane in 2 dimensions. And these are especially convenient when you have some sort of rotational symmetry, or when you have rotations around a fixed point. We're about to find out that treating x and y, sometimes it's completely fine, and it's not the optimal way, because it's sometimes a bit opaque, and instead using r and phi is even better in certain situations. Wonderful. So let's make some room now. No, I need to use this. Yeah, I'm gonna try and squeeze all this stuff up here. So now that we reviewed polar coordinates and their definitions, let's find out how to use them and why we use them. So you can think of the velocity, for example, of an object. And in Cartesian coordinates, we know that the velocity is in general, velocity is a vector. And this vector is actually the time derivative of the position vector. So this is the vector that has dx over dt and dy over dt as components. We're in 2D for now. Now, how does this vector look like in polar coordinates? So what are the components of this vector in polar coordinates? Well, I need to take actually a little step back, because see, the unit vector in the x direction, we call it x hat or I hat. This is simply the unit vector in the horizontal direction. And the unit vector in the y component is the unit vector in the up direction convention. As it turns out, for polar coordinates, the unit vector in the r direction is, well, actually, let me take this and see if I can move it around here. The unit vector in the r direction, I will draw it in red, is the unit vector precisely aligned with the direction of r. So this is r hat. And notice that it depends on whether the point P is. So it's not a constant it's not a constant. It's not always in the same direction, which might seem inconvenient, but I'll convince you, hopefully, that it's helpful sometimes. And similarly, the unit vector in the phi direction is perpendicular to it in the tangential direction to the circumference at that point. You can either trust me or spend some time trying to figure out that these have pretty simple expressions, these two unit vectors, if you're interested. And this is simply xy divided by r, or maybe let me write this as 1 over r x comma y. So these are the Cartesian components of that unit vector. Okay. And phi instead has components minus y and x, again divided by r. You can probably see almost by eye that these two are perpendicular, because if you imagine to take the dot product of these two, you would get 0. And because it would be minus xy multiplying the first components and then plus xy, so it would be 0. And yeah, another way to express these, which is also useful. Let me make some room by moving this stuff away again. Another equivalent expression for the unit vectors is the following, namely r hat is simply cos phi sine phi in the x and y components, and the unit vector in the phi direction, namely the tangential direction, is minus sine phi cos phi. This is important and useful to remember, just in case you get confused sometimes as to what the radial direction. Let me write this down. So this defines the radial direction, and this defines the tangential direction. All right. Okay, wonderful. Let's move on to the next page. Now, what about velocity? So I had started this conversation by saying, well, velocity, typically we write it as the time derivative of the position vector. As it turns out, in polar coordinates, we can split, so in the same way as in Cartesian coordinates, velocity has a x horizontal and a y vertical component. In polar coordinates, v has a radial component and a tangential component. So anytime you look at your axes, a point P and a certain velocity, see, this velocity has a component which is along r, and a component which is along the perpendicular axis to r, which is actually the phi axis, right? And in particular, well, this arrow is not very, doesn't look very accurate now, but so this would be v in the tangential component, and this would be v in the radial component, right? As it turns out, the radial velocity is none other than the rate of change of r, the magnitude of this vector r, okay? Maybe unsurprisingly. This is the radial velocity. The tangential velocity, either vt or v phi maybe, this is, remember that this is the angle phi, it's equal to r times the rate of change of phi, right? And this is the tangential velocity. Does this make sense? All right, let me rewrite this with a slightly better handwriting. Okay, so d phi over dt is how quickly the angle phi is changing. And it makes sense that the tangential velocity is proportional to this, because the faster you rotate, the faster the angle changes, the faster you're moving. But angular velocity, actually I'm hinting at a new quantity that we'll define just now, and physical velocity are not the same thing. There's there has to be a physical length in between, and this physical length is r, namely how far you are from the pivot, from the center of this rotation. So I hope you're not too shocked that this is the case, and and I hope you start familiarizing with this or these two expressions. So the time derivative of the distance r from the center, that's the radial velocity, and r, so the current distance times how quickly the angle is changing, this is the tangential velocity. The total velocity v, let me shrink this stuff. The total velocity vector is then, as usual, the combination of the two. So the total v would be vr in the r direction and v phi in the phi direction. Let's be very careful. This is not at all the same as saying that the speed, for example, is vr plus v phi. This is very, very wrong. You probably can have the intuition that instead, as usual, it's Pythagoras that tells us what the speed is. So the magnitude of v, aka the speed, is the root of vr squared, the radial velocity, plus the tangential velocity squared. Okay. Very nice. Moving on. I mentioned just now, I teased these words, angular velocity, and this is one of the most crucial concepts from week 1 in mechanics, and typically denoted with omega. This is one of the Greek letters for O, omega, the lowercase omega, and this is the rate of change of the angle phi. Okay, actually I'll take this moment also to talk about notation. I'm sure I'll repeat this many times, but in this course I use a dot as time derivative. Okay, so, and 2 dots, for example, for second time derivative. So, for example, x dot, this means dx over dt. X double dot means the second derivative of x with respect to t, and so on and so forth. I doubt it will go to 3 dots ever, but yeah, this is pretty standard notation for in sort of more advanced treatments of classical mechanics, and I hope you familiarize with this soon. It's very compact, so I quite like it. So another way of writing this definition is that this is phi dot. Okay, very nice. And this has like outstanding importance in what we'll see. To re-express what we talked about, what we said about velocity, physical velocity in these new terms, again, the radial velocity is still dr over dt, so r dot, and the angular, the tangential velocity is, we said it's r times d phi over dt, so it's r omega. This is the more standard way of writing velocity. R omega. Very nice. What are the units of omega? Well, it's an angle divided by a time. So it's, well, in general, any angle divided by time are the correct physical dimensions. So in SI units, this would be radians over seconds. Okay. Radians over second. Because radians are formally, it's kind of dimensionless, you can also find just 1 over second as your unit. Okay. Yeah, not to be confused with hertz, for reasons that are more historical than physical, but hertz typically relates to frequency, which is a different beast that we'll talk about in a second, but it's not quite the same thing. Okay. All right, maybe it's time to do a very quick exercise, if you guys are happy with that, using these type of things that we talked about. For example, let's say that you have coordinates x and y that are 3 and 4. Okay. What are my polar coordinates? And vice versa, what if I have polar coordinates of r and phi, which are, I don't know, 3 and pi over 3? Then what are my Cartesian coordinates? This is exercise 1 and 2. All right, let's do 1. Very quickly, so x and y, so r is root of x squared plus y squared, and so this is the square root of 3 squared plus 4 squared, and this is conveniently the root of 25, so it's 5. So the distance from the center of that point is 5. What is the angle? This is the arctan of 4 over 3. And to be completely honest with you, I don't know how much this is, but I can probably ask my computer. What is the arctan of 4 over 3? It's 0.93 or 927, let's say. And this would be in radians. Radians is what? Something like 57 degrees. So I'm guessing this is what? 53 degrees or something like that. We could actually do this by multiplying by 180 and divided by pi, and so this is 53 degrees. Wonderful. exercise 2, now instead I have r equals 3 and phi is pi over 3. This means that x is r cosine of pi, so it's 3 cos of pi over 3, which is 1/2, so it's 3 over 2, and y is r sine pi, and this is 3 times root 3 over 2, so this is 3 root 3 over 2, 3 root 3 over 2. Okay. Shall we do another exercise related to velocity, maybe? Yeah, that could be a nice idea. So an angular velocity. We could say, for example, that that could be nice. An object has a radial velocity of 2 meters per second and a tangential velocity of 1 meter per second. Okay. I want to know, 1, the speed of the object, and 2, the velocity vector in Cartesian coordinate when, well, let's say when 2a, when the position of the object, when the object is in 1, 0, at coordinates 1, 0, or when the object is in, what do we, 0, 1, for example. Okay. All right, let's see. So number 1, let's solve this exercise. The speed is simply Pythagoras, so the square root of VR squared plus V tangential squared, or V phi maybe, squared. And so this is the square root of 2 squared plus 1 squared in meters per second. So this is root 5 meters per second. Very nice. Now for the tricky bit, 2a. Okay. So we know what the radial velocity and tangential velocities are, but the direction depends on where you are. See, imagine that we have this point on in this coordinate system. So if I'm here and I have a radial velocity of 2 meters per second plus a tangential velocity of 1, it means that my velocity is going in this direction. However, if I'm in this position with, again, a radial velocity of 2 meters per second plus a tangential velocity of 1, okay, now my drawing is not as nice, but the velocity is completely in a completely different direction. So it can be counterintuitive to think, well, if I have the same radial component and same tangential component, then the vector must be the same, but it's not true. It depends on where you are, because the very sense of radial depends on where the radius is pointing, right? But we can calculate it. For example, in 2a, so the object is in 1, 0, so the r unit vector, so the velocity is VR in the r direction and V phi in the phi direction. R hat, the unit vector in the radial component, is cos phi and sine phi, so it's simply 1, 0. and phi is minus sine phi cos phi, which is 0 and 1. So in this case, VA is none other than VR in the x direction and V phi in the y direction. So this would be 2 and 1 meter per second, as we can see over here. If we work at 2b very quickly, oh, I forgot to shrink some of this. Well, I'm never gonna, oh yeah, pretty decent. Let's see if I can do this. Oh, well, it's close enough. And this one here is this. For 2b, now the r component is cos phi and sine phi, which for this being phi is pi over 2, so cos is 0 and sine is 1. And this is minus sine phi cos phi, which are none other than minus 1 and 0. All right. So V, no, and 0. So my velocity vector in B is, again, VR in the r direction and V phi in the phi direction. And you can probably figure out that this is minus V phi and VR, or minus 1 and 2 meters per second. And this is probably evident here. It's going at 1 meter per second in the negative x direction and at 2 meters per second in the positive y direction. All right, this concludes this this video. Thank you for watching. I'll see you soon.